This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 06, Second Law, Entropy and Isentropic Efficiency. Very high yield, 3 to 4 questions, and the highest impact trap in the course. Real turbines and compressors aren't isentropic. The exam almost always gives an efficiency below 1, and the scoring difference between applying it and forgetting is huge. Here's the problem. Steam enters a turbine at 5 megapascals, 500 Celsius, exhausts to 50 kilopascals. Isentropic efficiency 0.85. Find the actual specific work, the outlet quality, and the entropy generated per kilogram. The canonical PE isentropic efficiency problem, 2 steps. The ideal isentropic case first, then correct for efficiency. Every real turbine, compressor, and pump problem follows this shape. The second law has 3 equivalent forms. Kelvin, Planck. No heat engine runs on a single reservoir. You need a sink. Clausius. Heat doesn't spontaneously flow cold to hot. The entropy form, ds, is at least delta Q over the boundary temperature. Quantifies it. Equality for reversible processes, inequality for real ones. Entropy generation is always non-negative. 0 is the ideal limit. Every real process worse. Entropy on the TS diagram. For a reversible process, delta Q is T times ds, so area under the curve is heat transferred. Isentropic is a vertical line, isothermal horizontal. For a real turbine, the ideal path drops vertically to 2s. The actual curves right as entropy rises. That horizontal gap from 2s to the actual 2 is S generation per kilogram. Read it off the diagram. Entropy change formulas. For an ideal gas with constant specific heats, delta S is CV times ln of the T ratio plus R times ln of the volume ratio, or equivalently, Cp with the pressure ratio. For water or steam, it's tabulated. SF plus X times SFG in the two-phase region, or read from the superheated tables. For incompressible liquids and solids, the pressure term drops, leaving C times ln of the T ratio. For swings over about 500 Kelvin, use variable Cp. Isentropic efficiency. For a turbine, efficiency is actual work over ideal. The actual enthalpy drop over the ideal. For a compressor or pump, it flips to ideal over actual, because real compressor work exceeds ideal. Typical values run 0.70 to 0.95. 2 labels. 2s is the ideal isentropic outlet. 2 is the actual. Build the variable table. 3 state columns: inlet, ideal outlet 2s, actual outlet 2. Pressures pinned: 5 megapascals in, 50 kilopascals at both outlets. The outlets share pressure, but differ in everything else. 2s shares entropy with the inlet. The isentropic condition. Fill in givens, resolve state 1, then 2s, then 2 via efficiency. Pattern recognition. Isentropic efficiency below 1 always triggers the 2-step solve. Ideal 2s first, then correct with eta. Compressor and pump efficiencies flip the ratio. Adiabatic alone isn't isentropic. You also need reversibility. A final ask for entropy generation means finish with S actual minus S1. Handbook quick reference. The second law chapter holds Kelvin, Planck, Clausius, the entropy definition, and the entropy change formulas. The isentropic efficiency formulas are not there. They live in the cycles chapter. Today's steam problem also needs the SI steam tables. Solve. State 1. 5 megapascals, 500 Celsius. Superheated, since Tsat there is only 264. From the superheated table, H1 is 3434.7, S1 is 6.977. State 2s. The ideal isentropic drop sets S2s equal to S1, 6.977, below Sg at 50 kilopascals, so 2s is two-phase. Quality S2s minus SF over SFG is 0.905, and H2s from HF plus quality times HFG is 2427.3. Always phase check first. Had S2s exceeded Sg, 2s would be superheated. Step 3. Apply the efficiency. Ideal work is H1 minus H2S, 1007.4. Actual work is eta times that, 856.3. Less, since a real turbine delivers less than ideal. Actual outlet enthalpy, H1 minus the actual work, is 2578.4, still two-phase. Actual quality is 0.97, drier than ideal, since irreversibility adds heat back in. Actual entropy is 7.40. Step 4. Entropy generation. For an adiabatic steady flow device, S generation is just S out minus S in, 7.40 minus 6.977, or 0.43. Positive, as any real process must be. A non-adiabatic device would subtract Q over T boundary. Final answers. Actual specific work, 856. Outlet quality, 0.97. Entropy generation, 0.43. Backcheck. Actual over ideal work equals 0.85, matching the given efficiency. If it doesn't match eta, you made an arithmetic error. Traps. 5 ways this problem loses points. 1. Don't skip the efficiency correction. An efficiency below 1 is mandatory, and skipping it costs 15% on the work. 2. Flip the compressor ratio. It's ideal over actual, since real compressor work exceeds ideal. 3. Don't use S2S as the actual state 2 entropy. They match only in the ideal case, and the real state 2 has higher entropy. 4. Phase check both 2S and 2, usually both two-phase, not always. 5. Entropy generation compares actual outlet to the actual inlet, the same state in all 3 columns. Quick recall summary. Second law in entropy form. S generation is always non-negative. Delta S, ideal gas uses Cp and R with temperature and pressure ratios. Two-phase uses SF plus quality times SFG. Isentropic efficiency is actual over ideal for a turbine, ideal over actual for a compressor. Solve in 2 steps. Ideal 2S first, then actual 2 via eta. For an adiabatic device, entropy generation is outlet minus inlet entropy. Next up, Topic 7, Carnot and reversible cycles. The Carnot cycle sets the second law as ceiling, the highest efficiency any cycle can reach between 2 fixed reservoirs, the benchmark every real cycle is measured against. Before the next video, recompute today's problem with eta of 0.95. How much more work? How much less entropy? PEPrepengine.com/beta. The second law and isentropic efficiency cheat sheet, the worked problem PDF, and a 5-question quiz are attached. If the course helps you, subscribe.
The full study guide with every equation and common exam trap is free at PEPrepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.